Good afternoon, learners. I am Dr. Munish Bharadwaj from School of Engineering and Technology, and in the process of video conferencing sessions on ACPDM program, today the topic of the video conferencing session is operation and maintenance. This topic is related to the first course, BEE 001 and block 2, operation and maintenance. In this block we have 3 units. Unit 1, introduction to power distribution system. Second unit is substation equipment and distribution lines, and third unit is distribution transformer. On these 3 units we will have our expert Madam Anjali Chandra here, who will cover these 3 units today and also tomorrow. She will give a glimpse of all these 3 topics today and discuss some of the things in detail today and some of the things on tomorrow. Now I request Madam Anjali Chandra to take over and start the session.
Good evening, friends. We will start with introduction to distribution systems, and as you all know, how will the slides come? As you all know, the power distribution system starts from the generation, transmission and distribution, and we have the generating units. The slide is not coming.
Yes, slide will come.
Okay. We have the generation system, then we have the transmission lines, and then we have the distribution system for taking power to the consumer. So we are basically dealing with the distribution systems, which can start from the sub-transmission level, which is the 33 and 66 kV level. We go on from the 33 and 66 kV level to the 11 kV lines, and then to the distribution system, which consists of the distribution transformers and the distribution feeders. And from the distribution feeders and from the poles, we have service connections taking the power from the pole to the consumer. So we divide this power distribution system into the transmission system, which is the grid substation, which consists of 220, 132 and 66 kV grid substations. The sub-transmission network, which starts from the 66 and 33 kV substation, then from where the power is stepped down to 11 kV, and from there we have the 11 kV primary distribution feeders, on which we have the distribution transformers, which are known as the distribution substation. The power is further stepped down by 11 by 0.4 kV transformers to the utilization voltage of 415 volts, and then we have the secondary distribution network. It carries power from the distribution substation to various consumers through service lines and cables. So the traditional distribution system has been low voltage distribution system, in which we have big capacity distribution transformers, which may be of the rating of 1000 kVA, 630 kVA, 500 kVA, 400, 250 or 230 and 100 kVA, and we have the LT lines, which are long and lengthy, which take power to the consumer. This type of system has been contributing to very high losses in our system. As you all know, the losses, transmission and distribution losses in our country are of the order of 31%, and that too are very high as compared to what is prevalent in other countries, the advanced countries of the world, where the losses are of the order of 6 to 11%. So this traditional system of taking power to the consumer on low voltage lines has been contributing to very high losses due to large voltage drops with over the LT lines, high line losses, voltage fluctuations, and giving an opportunity to the consumers to hook the lines. It's very easy to hook the LT lines and cause theft, and this has been causing very high commercial losses in our system. All of us know that the consumers have been hooking the system through the LT lines, and they are putting kundis or what you call hook on the LT line and taking power directly throughout without a meter, which causes a huge amount of losses to the utility. This is a photograph which shows how people are hooking LT lines in our system. There is another photograph here which clearly shows the jumbling of lines and hooking and losses caused to the utility, which is a very serious menace in the low voltage distribution line. The voltage at the consumer end is very low, and it is causing a lot of commercial losses as well as high technical losses to the power utility. So we now prefer to go in for the high voltage distribution system. The high voltage distribution system differs from the low voltage distribution system in that we use small capacity transformers and have less of LT, or you may call it LT less or less of LT, because it is very difficult to have LT less, so we call it less LT system, where the transformer is of very small size with 5 kVA, 10 kVA or 16 kVA, and a few consumers, maybe 3 or 5 or 10, are connected to the transformer, and very small LT line is taken to give power to the consumer, and that LT line is also not bare. Mostly it is taken through aerial bunched cable, and it is difficult for the consumers to hook an aerial bunched cable. It is very easy to hook on a bare conductor, but it is very difficult to hook a aerial bunched cable. So that is why we are now moving to high voltage distribution system. Secondly, the voltage is improved. The losses on the LT line are proportional to I square R, and in a high voltage system the I reduces quite a lot by taking the 11 kV line right to the consumer's premises, and therefore the I square R losses reduce substantially. The commercial losses reduce substantially, because when there are only 4 or 5 consumers on a small transformer, it is very easy to identify the persons who are doing theft, and the voltage is also improved because the 11 kV line is very near to the consumer, and the consumer is not distant from the transformer. So the advantages of having a high voltage distribution system is tremendous, and we are now going in for high voltage distribution system under the APDRP program and the RGGY, Rajiv Gandhi Gramin Vidyutikaran Yojana. Most of the schemes now being prepared are with the high voltage distribution system. When you convert high voltage distribution system, then you can convert the existing LT line also to 11 kV line, and introduce small capacity distribution transformers in the line, and use aerial bunched cable for giving the connections. With this type of system, you will have a system like what is shown in the slide. You have a very small transformer which can be hooked directly to the pole. It is a very small transformer as compared to the conventional big transformers which are being used like 1000 kVA, and you can see the weight and size of the transformer is very small, and it may be even hooked to the pole through a single bolt. There are certain transformers which are so low in weight that they can be hooked directly to the pole through a single bolt. This is another slide showing the high voltage distribution system connected outside the consumer premises, and since the transformer is very small, the consumer also should not have any problem in having it very near to his house. It is aesthetically also very much better than the low voltage distribution system. This is a small three-phase 25 kVA DTR, which is also used in high voltage distribution system. The high voltage distribution system can be single phase or 3-phase depending upon the type of loads which are to be fed. If they are motor loads, then 3-phase 25 kVA distribution transformer can be used. If they are single phase loads, then single phase high voltage distribution system can be used. The choice of method will depend upon the type of loads to be used and the load density in the area. So when you compare the costs of a conventional system LT distribution system and a high voltage distribution system, then with the LT overhead bare and LT underground system, the cost is 1:1.5, 1 and 1.5, and HVDS high voltage distribution system, if the cost of LT is 1, then the cost of HVDS overhead system is 1.4 times the cost of the LT distribution system, and the cost of HVDS with aerial bunched cable is 1.5 times, and it's comparable to LT underground. But the advantages of high voltage distribution system are many, and it would be better to go in for high voltage distribution system with aerial bunched cables. And the payback period for such a system is around 3 to 5 years, and it's very easy to get back because the losses reduce tremendously with the high voltage distribution system. So project on HVDS was carried out by CPDCL Hyderabad, and in this 3 number transformers of 2 into 100 kVA and 1 into 63 kVA were replaced by 15 transformers of 25 kVA. And you'll see the things which had been replaced. The DTR of 63 kVA was replaced by 5 into 25 kVA. The LT line was replaced by HT line of 1075 meters, and it was reduced by 1275 meters. The HT line had to be increased by 625 meters, and total reduction was around 660 meters in the line HT plus LT combined. And the parameters before HVDS and after HVDS were that the system demand reduced from 109 to 79 kilowatt. That means the commercial losses came down substantially. People who had been stealing were now not able to steal. From 80, the demand reduced by around 30 kilowatt just by putting in a high voltage distribution system. The consumer voltage improved from 350 volts to 411 volts, and the energy saving per year was around 29,000 units. So going in for a high voltage distribution system as compared to a low voltage distribution system offers advantage in terms of reduction in losses, in terms of improving the voltage, and in terms of energy saving, and losses reduced both on the technical front as well as on the commercial front. So the advantages observed have been reduction of LT overhead line loss, then preventing hooking and bringing unauthorized consumers into the billing net, better voltage profile, and also reduction in interruptions, because whenever the LT lines are there, there is a lot of fault on the LT line, but on the HT line the faults are much less, and the consumers affected by a fault are much less because the LT line associated with a small distribution transformer is very low as compared to the LT line associated with a large transformer. We'll go on to the next presentation now on substations and lines. This one. Now we'll introduce you, we have told you about the types of distribution systems, but the equipment used mainly in the distribution systems. As told earlier, the distribution systems start from the sub-transmission level, which is the 33 or 66 by 11 kV substation, and the main equipment used in a substation are the power transformer, the bus bar, the structures for the equipment, the switch gear, the control, protection and monitoring equipment, the earth mat, the automation system, and the site support facilities. These are the major equipment used in a substation of 33 by 11 kV or 66 by 11 kV, which is the sub-transmission level, from where our power distribution system starts. So the power transformer is the first major equipment, the most vital equipment and the costliest equipment for a 33 by 11 kV substation. The power transformer may be 3-phase or single phase, but generally it is 3-phase, and usually we take 3-phase and take single phase only where there is a transport limitation. The weight of the transformer maybe it may be difficult to take on a hilly terrain like maybe in Leh or Himachal, but otherwise we have a 3-phase transformer. We have a 2-winding transformer, and we have on-load or off-load tap changer on the power transformer. When we go in for transformers, there will be a separate lecture on transformers. Then we'll go in detail about the power transformer and the distribution transformers. At the moment, we'll just discuss what are the major equipment being used in a substation. And the next major equipment for a substation is a bus bar. And the bus bar may be made of a conductor or an aluminium pipe. The conductor may be all aluminium conductor, all aluminium cored steel reinforced conductor, triple AC conductor, and the choice will depend on the type of reliability you want to have in the substation and the cost and the current to be carried by the conductor or the bus. Then the space for a bay will depend on the phase-to-phase clearance and the safety clearances required in the substation. And you can see a photograph of a bus bar in the slide. The next major equipment, the bus can be in a single bus scheme. There are various schemes available for the bus bar. It may be a single bus, it may be a double bus, it may be a single bus with sectionalizer, it can be a double and main transfer bus, depending upon the importance of the substation, the safety and reliability required. The single bus scheme is the most simplest and cheapest bus bar scheme. Maintenance and extension of bus bars are not possible without shutdown of the substation, and operation and maintenance of bus bar is easy, however. So in the rural areas, mostly single bus scheme is being used. Then we have the circuit breaker. The circuit breaker is a non-load mechanical switch used for making, carrying and breaking currents under normal conditions and breaking under abnormal conditions. The circuit breaker may be of the oil type, the minimum oil circuit breaker, air blast circuit breaker, SF6 circuit breaker, or the vacuum circuit breaker. Earlier we were using bulk oil circuit breakers, but now we are not using bulk oil circuit breakers because they are difficult to handle and cause fire whenever there is a blast. So we are now going in for mostly vacuum and SF6 breakers at the 33 kV level. The operating mechanism of the circuit breaker may be hydraulic, pneumatic or spring type. Then we have the isolators in the substation. The isolator provides a visible air gap isolation of equipment and feeder sections for safe examination, maintenance and repair. It is capable of carrying normal current and short circuit current for a specified time. The isolator may be of the horizontal center brake type, the double brake type, the pantograph type or the vertical single brake type. These are various types of isolators. The earth switch of an isolator is a mechanical switching device for providing safety earthing during maintenance. It is capable of withstanding short circuit current for a specified time. Then in the substation we have the instrument transformers, which are the current transformer and the potential transformer. The current transformers are devices used to get the replica of primary current, which shall be suitable for the measuring instruments and the protective relays inside the substation. We need to measure the current and voltages and operate the relays. For that we use a current transformer, and the number of cores in the CT are as per requirement. Usually the CTs are of 1 ampere or 5 ampere depending on the requirement, and these 1 ampere or 5 ampere CTs provide current to the meters and to the relays for measuring and protection. Then we have the potential transformers. These are used to get the replica of the primary voltage, which shall be suitable for the measuring instruments and protective relays, and the number of cores are as per requirement. So both the current transformers and protection transformers are basically for the measurement and protection of the substation. Then we have the surge arresters. And the surge arresters generally used now are made of ZNO disc, and these provide protection against lightning and over voltages and surges, and they are designed with respect to their energy capability and pressure relief capability, and they have to operate to protect the equipment in the substation whenever a lightning strikes the substation or whenever there is a surge in the voltage. Then we have shunt reactors or reactive compensation connected to the line or the bus for control of over voltages and for control of the power factor. Usually the power factor at various substations is around 0.8 or 0.7 at 33 by 11 kV, and to bring this power factor to the level of 0.9 or 0.95, we use shunt reactors on the substations. These are usually connected to the 11 kV bus of the substation, and the requirement is worked out through system studies. They are usually in the term of capacitor banks. They can be of the automatic type or of the manual type. The automatic switched capacitors are best used on the 33 by 11 kV substations because they provide compensation with which is according to the requirement of MVR at that point of time. If we do not have switched compensation, then we use fixed compensation, and that fixed compensation should be such that it does not make the power factor leading while on off peak. If it makes the power factor leading, then again we are running into trouble. So therefore fixed compensation usually is not provided on 33 by 11 kV substation. It should be switched type of reactive compensation. Then we have control and relay panels in the substation in the control room building, which provide for transformer protection, shunt reactor protection, and the subtransmission line protection. On the transformers, we have the differential protection, the overcurrent and earth fault protection, and the REF protection if the transformers are more than 6.3 MVA. Then we have the shunt reactors or the reactive compensation protection, which can be differential, overcurrent and earth fault and REF. Then the subtransmission line protection, we have one main protection and the overcurrent and earth fault protection. Then we, in the control room building, we have the control relay and protection panels, the batteries, the battery chargers, the main switchboard, the AC distribution board, the DC distribution board, lighting transformers, lighting distribution boards, rooms for the station in charge and staff, and other miscellaneous equipment are placed in the control room of the substation. Then we have an earthing system in the substation, which the purpose of the earthing system is to provide for safety of the living beings around the vicinity of the substation and proper functioning of the protection system under fault condition, and to limit the touch and step potential within tolerable limits. We have an earth mat, as you know, inside the substation switchyard, and the design of the earth mat should be such that the touch and step potentials are within limits, and we do not get a shock. The personnel do not get a shock, and the equipment in the substation is safe. Then we have the station battery, which provides a source for operating control system equipment during system disturbances and outages. Normally 24 or 30 cells consisting of lead acid or nickel cadmium batteries are provided. And this is about the 33 by 11 kV substation. Then we have the 11 kV feeders. We'll come to the feeders and lines later on, but from the 11 kV feeders, we have the distribution transformers, which provide step down to the consumer voltage. So the distribution substation consists of the distribution transformers, its mounting structure, lightning arresters on the distribution transformers, and LT distribution box, protection system for the distribution transformers, LT cables, and reactive compensation is now being provided on distribution transformers as well to control the power factor and the MVR drawl from the system. So the transformers, distribution transformers are of various ratings, as we earlier also said. The distribution transformers can vary from ratings from 5 kVA to 1000 kVA, and usually smaller kVA transformers should be preferred so that they can be placed nearer to the load center and the losses are less. And we'll come to details of distribution transformers when we come to transformers. So the mounting structure of the distribution transformer can be mounted directly on a pole, as we saw in the HVDS, or the distribution transformer can be mounted on two poles, which is called an H-pole mounting, or the distribution transformer can be placed on a plinth. These three types of mountings are usually used for the distribution transformers. I show you photographs of these types of mountings. You can see a single pole mounting of the distribution transformer. The distribution transformer is directly mounted on the poles. It can be single phase or three phase. This is usually done for small transformers which are mounted on the pole. Higher capacity transformers have a higher weight, so they are mounted usually on H poles like this. Two poles are placed and there is a channel in between the two poles on which the transformer is placed. So this is a H pole mounting of a distribution transformers, and this is on the ground, which is also called, usually there is a plinth. This is placed on the ground where there is usually a plinth on which the distribution transformer is mounted. So these are the three types of mountings which we usually use for the transformers. The direct mounting is used for transformers up to 25 kVA. The H-pole mounting is usually used for transformers up to 250 kVA, and the plinth mounting is used for transformers from 250 kVA to 1000 kVA. Even though smaller transformers can also be placed on the plinth, but these are the general guidelines. So for protection of these distribution transformers, we use lightning arresters, 11 kV lightning arresters, 9 kV rating, outdoor type, and these are used for diverting the lightning surges to earth. The lightning arrestor usually installed on the HT side of a distribution transformer, but the practice in our systems has been that we have not been installing lightning arresters on the distribution transformers, and the distribution transformers have been failing due to voltage surges on the distribution transformers. We should be installing lightning arresters, but it has been observed in most of the utilities that the utilities do not install these. They just place the distribution transformer. Then the protection system being used for distribution transformers is that the HT side of all distribution transformers is normally protected by dropout expulsion type fuse. 3-number 11 kV dropout fuse unit comprising a set are installed on the mounting cross arm. And for LT side, we are usually using fuse or MCCB or MCB. But generally the fuses are used, and that too usually the practice has been that the fuse is placed of a higher size so that it does not blow off. It is people prefer that the transformer should blow off, but the fuse should not blow off. So usually even if we put an MCB and MCCB, then people tend to put something inside the MCCB to hold the MCCB in place and it doesn't blow off. But it would be a better practice to install MCCB or MCB on the low voltage side to protect the distribution transformer. For transformers below 100 kVA, some switch fuse unit or wire fuse is used on the low voltage side. Then we come to the feeders. The definition of a feeder is that the feeder consists of all primary or secondary voltage segments of distribution lines between two substations or between a substation and an open point. That is the definition of a feeder. The feeder may be of 11 kV feeder or the LT feeder. The 11 kV feeder emanates from the 33 by 11 kV or the 66 by 11 kV substation, whereas the LT feeder emanates from the distribution substation or the distribution transformer, from the LT bus of the distribution transformer. The feeders are connected in a configuration which depends on the type of network required in the distribution system. Generally, three types of network are normally available in the electrical distribution system, which are the radial, the loop, and the cross loop network, and sometimes we have a mesh network. On the 33 kV side, generally we have a weakly open mesh. We usually have a radial system in the 33 by 11 kV and the LT systems, because generally these, when you provide in a loop, the system is much more costly, and we do not go in for mesh. Only in where reliability is required, we use a mesh system or a ring main unit. So I'll try to show you the differences between a radial distribution system, a loop distribution system, and a cross loop network distribution system. In the radial distribution system, there is a single path to each group of customers. The cost is lowest. It's simple to plan, design, and operate, and usually used in rural areas. In a loop distribution system, there is a double path to each group of customers. The cost is medium. It is moderately simple to plan, design, and operate, and it is used in urban areas. In a cross-loop network distribution system, there are multiple paths to each group of customers. It's a high-cost system, complex to plan, design, and operate, highest reliability, used in large cities and for critical loads, and it is used in bigger cities and bigger urban agglomerates. So the distribution feeders can be overhead or underground. Both types of systems are being used. Each has its own relative merit and demerit. We'll go into overhead lines and underground cables separately. So we'll first start with overhead lines. The main equipment used in overhead lines are supports, insulators, conductors, cross arms, and clamps of various types, stay sets, stay wire, strain hardware sets, and earthing sets, and maybe spacers. So these are the main equipment used in the overhead lines. You can see this is an example of an overhead line going. So the insulators resist the flow of electricity, and insulators keep electrical current from energizing the power pole. Basically, the insulators carry the conductor, and the type of insulators used in connection with overhead lines are shackle type insulators, pin type insulators, suspension type, guy strain insulators, and post type. So these are the various types of insulators being used, and the type depends on the voltage and whether it is a dead end, whether it is a tangent location, where the pole is being used. It depends on that. The shackle insulators are mainly being used on LT lines. The pin type are being used on 11 kV and 33 kV lines, and the suspension type are generally being used on tangent locations. The guy strain insulators are used in the stay sets, and the post type are used in the substations. So this is a photograph of a pin type insulator. You can see what an insulator is looking like. And then we have the strain hardware set. The conductor is strung between sections through a strain hardware set. It is put on top of the insulator. It is fixed with the insulator, and if 3 discs are used for 33 kV, then the strain hardware set is fixed at the end of the last disc. It is made from malleable iron or aluminium alloy, and set with aluminium alloy is preferred to keep losses minimum. Then we have the stay sets, and you people have already seen a stay set. The guys of standard galvanized steel are used on the terminal, angle, and other such poles, where the conductors have a tendency to pull the pole away from its true vertical position. The stay set is used where the conductors have a tendency to pull the pole from its vertical position, and transverse guys perpendicular to the direction of the overhead line are used when the poles are located in sandy and waterlogged soils of low cohesive strength. The guys are fastened to the pole near the load center point with the help of pole clamps. The other end of the guy wire is secured to a stay rod embedded in the ground. MS or galvanized steel is used for these stay sets. The stay rod is located as far away as possible from the pole. Then we have the cross arms. The cross arms of hardwood or softwood or fiberglass are being used mostly. Steel cross arms are also being used and they last much longer. MS angle iron and channel iron sections are also being used for this purpose, and the shape and the length of the cross arms would depend upon the desired configuration of the conductors. The conductors may be in vertical, horizontal, so the shape of the cross arm would also depend on the configuration of the conductors. The principal types of line supports being used are wood poles, concrete poles. Concrete poles may be reinforced cement concrete or pre-stressed cement concrete. Then we have the steel tubular poles. We are also using rails or rolled steel joists as poles, and we also use lattice type poles for the distribution systems. Various types of poles, the use depends on the height, the voltage level, and the type of terrain in which you are going to put the system. The size and the height of the pole depends upon the span length going to be used, conductor size and tension, voltage level, phase and ground clearances. The forces acting on the pole are the self-weight, the weight of the conductors, the ice, wind pressure on pole, cross arms and conductors. And the planting depth varies from 1/6 to 1/10 of the pole height, and usually the planting depth is between 1500 centimeter to 1800 centimeter. Then the major equipment is the conductor, and the conductor is classified as the material that allows the flow of electricity with minimal resistance, and aluminium and copper are mainly being used for the flow of current. The two metals that are mostly used are copper and aluminium. They are the conductors of choice because of their non-magnetic characteristics and of course their low resistivity. Then we have the earth sets, and two types of earthing arrangements are being used with GI pipe and with GI wire, and GI pipe is 40 mm dia and 2500 mm long, and 8 SWG GI wire is used with 115 turns which are closely wound. Binding dia is 50 mm and length is 1500 mm. These are the two types of earthings used with poles. Then we have the guard wires. The guard wires are generally used at all points where a line crosses a street, road or railway line, other power lines and telecommunication lines. As per IE Rule 88, the guard wires of galvanized steel of minimum 4 mm dia having breaking strength not less than 635 kg should be used and should be fitted on structures on either side of the crossing. Guard wires should fully cover the phase wires and accordingly should not be more than 30 centimeter away from the outer phase wires. So basically the guard wires are so that no phase conductor falls down. Then these were the major equipment being used in a overhead line, and the configuration of the line can be horizontal, vertical or delta. The vertical configuration is not suitable for cold regions as ice coating around conductors may disappear on one conductor but not all, causing unequal sag which may result in a short circuit between them. So the three types of configurations being used are horizontal, vertical and delta for the overhead lines. Then the next system is the underground cables. As we earlier said, the feeders can be either overhead or underground. So the overhead lines we have already discussed. We now move over to underground cables. Underground cables are sometimes preferred due to elimination of outages by abnormal weather conditions, and the system is more aesthetic. So we'll come to the difference between underground and overhead lines. What is the difference? When we consider overhead versus underground cables, then the cost of installation in an overhead line is lesser initially, and the installation is also easy. In the cables, initial cost is high and needs more time for installation. Approximately 10 times the cost of overhead line of same voltage and current carrying capacity for some same length. Then the cost of maintenance is high in an overhead line and low in cables. Breakdown and incidence of faults causing damage to equipment is more frequent breakdowns in overhead lines and minimum except for damage caused by other agencies in an overhead line. Restoration, supply can be restored in minimum time in an overhead line, and skills required for restoration are also minimum. But in cables it is very difficult to identify the fault, and rectification of the fault calls for high skills. Actually, a fault locator is required for identifying where the fault is in the cable. Generally, people do not even know where the cable is going, and it is very difficult to find where exactly is the fault. So unless you have a cable fault locating equipment, it is difficult to locate the fault in a cable. Then the interruptions are maximum in an overhead line and minimum in an underground cable. The losses are more in an overhead line because hooking is possible, and they are negligible in an underground cable, though there have been the reports of people stealing cables, but otherwise the hooking by the cables hooking of cables is negligible. Then in case of overhead lines, the accidents are much more, risk of life involved is very much more, whereas in cables it is very rare.
Sir, there is a call from Bangalore.
Yeah, we can take a call from Bangalore. Yes, Bangalore, please speak. Yes, Bangalore, please speak. Yes, please speak. Yes, Bangalore, please speak.
Sir, one question was there. Madam told that there are three configurations, that vertical, horizontal and delta. What are the criteria for selecting? What are the specific criteria? Means any specific thing on deciding it, or we have some standards?
And actually, the configuration depends on the right of way available, then the voltage level at which you are going to take the line. If you don't have right of way, you have very little space, then you can go in for vertical. If you have right of way, then you can go in for delta or horizontal configuration, and LT lines may be taken as horizontal, but it depends on the voltage level as well as the right of way available.
Do you want to say something in continuation, Bangalore?
Sir, that's slightly it's not audible, sir.
Oh.
Okay.
I think we will discuss in detail in the next lecture. Shortly we will have a break. After the break we will discuss these things in detail.
Maybe we can discuss this afterwards. So we'll continue with the difference between what happens in an overhead and underground cable.
Yeah.
So we were going in for accidents. In case of overhead line, the accidents are much more. You have birdage, you can have faults due to trees falling on the lines. But in cables, these are very rare. Then you can have the overhead line needs more land for installation of substations, and in case of underground, installations can be installed on minimum land, but costly due to need for ring main units. Aesthetically also, the underground cable is much better than an overhead line, but the cost of an underground cable is definitely much higher, so that is why we go in for overhead lines. And in cases where like in metros we are now using underground cables, the selection of the cable is done on the basis of the maximum permissible conductor temperature, the same conductor with the same conductor size, the maximum continuous current carrying capacity depends on the depth of laying, underground temperature, ambient temperature, proximity of other cables, types of ducts used and load cycle. The maximum permissible conductor temperature is as shown. For paper insulated lead card covered cables, for 33 kV it is 65 degrees C, for 11 kV it is 70 degrees C, for LT it is 80 degrees C, for PVC cables it is, for 33 kV it is 70 degrees C, for 11 kV it is 70 degrees C, and for LT it is 70 degrees C. For XLPE cables, permissible conductor temperature is 90 degrees C for 33 kV, 90 degrees C for 11 kV, and 90 degrees C for LT cables. The cables are designated as EHV cables for 66 kV and above, medium and HV cables for 3.3 to 33 kV, and LT cables for insulated 1100 volts cables. The initial cost of laying the underground cable system is very high, but as seen earlier, the maintenance charges are minimum and also they have a long life. It is estimated that the cost of underground cable system at any voltage and for the same current carrying capacity is about 10 times the cost of an overhead system. For the entire system, not for the cable alone. The jointings and terminations. The cables are supplied in reels of standard lengths. The straight through joints and end terminations are costly and need skilled staff. Special lugs and terminations are required for using cables. The types of terminations which are available are cast iron molded joints and terminations, epoxy resin type terminations, heat shrinkable type terminations, cold shrinkable type, and push-on type. The cast iron molded joints and terminations are no longer being used, and now we use the epoxy resin, heat shrinkable, cold shrinkable, and push-on type terminations for the cables. And then we have the meters for measurement of energy and other electrical quantities. These meters are installed at various points on the in the substation. In the substation, they are installed on the 33 or 66 kV incoming feeder. They are also installed on the outgoing 11 kV feeders. Then we are also installing meters now on the distribution substations for.
Question on AG set.
Yeah, please. Please give the
Yes,
question.
please.
Ma'am has discussed the installation of LT and ST overhead feeders
Yes.
and underground cables. Considering the size, strength and capacity,
Yes.
but the causes of interruption / fault
Yes.
in the overhead line has not been elaborated.
Yes, that will come later. We are, at the
Overhead
moment,
line may be
Yes.
11 kV / LT kV. One thing I will add
Yes.
that presently as in working in DSCS, I have just eliminated the interruption due to birthdays.
Okay.
On every DP, I have just installed a knife type system with yellow color paint,
Okay.
and a cable was also wrapped on the conductor to repel the birds.
Okay.
So I would like to just add that this must be also elaborated to all of these persons who are just in the maintenance system. Thank you. J.K. Garg.
Okay, thank you, Garg sir. Actually, as I told you in the beginning that this is in this topic we will be just give you the glimpses of the various topics or the systems in this power distribution system, and details we will cover in the next lecture after the break. We are having the 2 lectures also today, and tomorrow also 3 lectures. So details of these things we will be discussing later on. So because of that, madam has not discussed the details of these things. She will discuss later on. And as you told that the details, whatever you have done to prevent all these faults and these, madam will certainly highlight the things. So have patience and listen. Thank you.
Thank you, Mr. Garg, and I think it's a very good suggestion to use equipment to prevent birdage, and that has already been done in BSES, and I think there are people from BSES here who can explain what has been done. The yellow paint being used is quite good, and we'll listen to what BSES has done for preventing birdage. This is a glimpse of what are the equipment being generally used on overhead lines and underground cables. The basic equipment being used in substations, lines and cables.
Now I think we would like to have a short break.
Yes.
And now we will have a break for 10 minutes. After 10 minutes we again will assemble and listen to madam for the details of these things.
Yes.
Thank you.
Thank you.